This is the third part of the 21st lesson in heat transfer. In the 21st lesson, we have been looking at internal flow convection heat transfer when the duct in which the fluid is flowing is subjected to a uniform flux. In this third and final part of the lesson, we will look at how to calculate the surface temperature of the duct in which the fluid is flowing. By the end of this lesson, you should be able to give a reason why an engineer may need to calculate the surface temperature of a tube in which the fluid is being heated via a uniform flux applied to the wall. You should also be able to calculate the surface temperature of a tube in this case from knowledge of the flow conditions and an appropriate Nusselt correlation. On with the lesson.
The other thing that I think is something that a designer would have to do in thinking about how to build these parabolic trough concentrators would be, what's the surface temperature at the exit of the concentrator? Or, honestly, what's the surface temperature anywhere, right, along the length, right? Like, in any place, of course, knowing how much the fluid's heated up on average is important, but probably knowing the temperature of the absorber is also important. Why might that be important? Kate?
So you don't melt resistance.
Yeah, so Kate said, so you don't melt it. That'd certainly be true, right? If the absorber temperature was going to be higher than the melting point of the absorber material, then we're in trouble. Like, we have no more absorber anymore. It's gone, it melts. But even if it's not melting, imagine for material science, you learn something about creep, right? So things that are warm tend to creep faster. So this thing is 17 meters long, and it's basically a big tube, more or less pinned at two ends. So think about the creep that's going to happen, right, over time. The tube that started as a straight line over time is going to tend to bow and bow and bow and bow. So being able to know the temperature of the absorber is really important for predicting things like how much creep do we anticipate, because maybe we need to put some supports in the middle, yeah, so that we can control how much the deflection is to a level that's acceptable for us, say for making sure that the absorber doesn't move out of the focus of the concentrator. So that might be one reason you would want to know this value. So how do we get it? So notice that for predicting the mass average temperature in this particular case, we did not need heat transfer. The exercise we just went through was basically thermo, right? Like, you applied an energy balance, and we didn't have to bring a rate equation into the game. But this question requires us to bring a rate equation. So we need Newton's law of cooling here. So Newton's law of cooling is going to link the mean temperature to the surface temperature of the tube, because remember, we're swapping out T infinity for the mass average temperature in Newton's law of cooling. So I just told you we now can calculate this at any location. I'm given the flux, yeah? So the only thing that I'm trying to figure out what is the surface temperature. So what's left over is we need H. We need the convection coefficient for this problem. The convection coefficient is going to dictate what the surface temperature needs to be, right, based off of the mean temperature of the fluid in order to accommodate that applied flux. The larger the applied flux for some fixed value of H, the larger the surface temperature has to be. Yeah, or like another way you can think of it, the bigger the delta T has to be in order to accommodate that flux. So what's the H, like, what does H depend on? What do we need to do to get H? Where need to do might include things that we have to calculate or look up. Or what does H depend on, I guess, kind of. Okay, so I heard the Nusselt number, yeah. So another way we could state what do we need to get H, like, because the Nusselt is equal to H probably times the diameter in this case over the thermal conductivity. Another way I could state this question is, what do we need to get the Nusselt number, right? Because if I can get the Nusselt number, then I know I've got H. So what do you do to get the Nusselt number? What are some things that you had to do for external flow? Probably we need to calculate the Reynolds number, right? Why would the Reynolds number be important? It tells us what that? It tells us something about the nature of the flow. So the Reynolds number is going to allow us to say, am I laminar or am I turbulent? And probably knowing which one you are in the tube is going to be important for the convection, and thus important for H, right? Okay, so calculating the Reynolds number is going to be important. It's defined as, oops, not the convection stuff, density times the mass average velocity times the tube diameter divided by the kinematic viscosity. Now, in internal flows, it's going to be much more convenient most of the time to substitute in that the mass average velocity is the mass flow rate divided by the density times the area, right? Where the density times the area, in this case, is just density times pi fourth d squared. If you substitute that in, hopefully you see that the density cancels, one of the tube diameters cancels, and we end up with a 4 over pi. So I have 4 times m dot over the viscosity times pi times d. So if you look at the data that we were given for this particular parabolic trough concentrator, we had 4 times 2.5 kilogram per second over the viscosity we were given is 0.15, so 0.15 times 10 to the minus 3 kilogram meter second times pi times 0.07 meters, because it's a 70 millimeter tube diameter. So we calculate, do this, you do 3 times 10 to the 5. Okay, so the Reynolds number is 3 times 10 to the 5. So what does that mean for us? Are we laminar or are we turbulent here? Okay, you all say turbulent. This is good. So this is the most common mistake, I would say, that I see students make when they're first learning about convection heat transfer and internal versus external flow. You all said turbulent for very good reason. I 100% know why you said turbulent. You were thinking of this thing, Reynolds x sub c is equal to 5 times 10 to the 5. Okay, that's the Reynolds number that we used in external flow to tell us where the boundary layer transitions from laminar to turbulent. So a couple of things. This is for external flow. We don't have external flow. We have internal flow. Yeah. And the other thing is it tells us something about the transition point, right? So this tells us about a transition point. What it really says is the boundary layer has transitions to turbulent at this spot, right? So this isn't going to work for us, I guess, is kind of my point. So we're asking us kind of a different question. So all that's 100% true, but we can't use that to interpret this Reynolds number, which is a Reynolds number based off of the tube diameter, right? It's not a Reynolds number based off of some position away from the leading edge of a flat plate. It's kind of a different beast. So I totally get it, but this isn't not the number we're going to use. We have a different number to use for internal flow. Remember what that number is? 2300, yeah, thanks, Nick. So this number is much, much bigger than 2300, and 2300 is our cutoff for the nature of the flow inside of the tube based off of the Reynolds number calculated on the tube diameter. So in this particular case, we're going to choose, and we're going to say this has got to be turbulent because the Reynolds number is much, much bigger than 2300, a lot bigger than 2300 here, right? So 2 orders of magnitude bigger than 2300. So once you've done that, then, right, you're like, okay, I've got turbulent flow in this tube. If you know you have turbulent flow, you're in a tube, you're going to go look for what? We know that we wanted to get the Nusselt number. So we're looking for a Nusselt equation or correlation, right? We got to go find the right correlation for this particular case. So you're going to turn to your book, which I think I have open. So here is, here's your textbook in chapter 8. So I'm just, like perusing through internal flow section. I'm looking for what I'm looking for. Here, convection correlations, turbulent flow in circular tubes. Sounds like me, right? It sounds like us. That's what we have here. We have turbulent flow in a circular tube. So if you start looking then, okay, it says, oh yeah, turbulent flow is really damn complex. So we just have empirical correlations, and there's this classical correlation based off of this thing called the Kilton-Colburn analogy, which gets us to the Dittus-Folter equation. So you get down here, you don't have to understand any of that to know that this is what I'm after. I'm after a Nusselt number, right? So then I check, do my conditions for this particular problem match those for the correlation? Okay, so it says, I got this funny thing, N, says N is 0.4 for heating, or it's 0.3 for cooling. So are we heating or cooling in our parabolic trough concentrator? We're definitely heating, so we're going to use N equal 0.4. And then we have to look at the conditions where it applies. Is our Reynolds number bigger than 10 to the 4? Yes. Is our tube more than 10 times long the diameter of the tube? So the diameter is 0.07. Our tube is 17 meters long. Most definitely, yeah, like it's much longer than that. And do you remember what is the significance of this 10? It's not coincidence that it's 10. This is turbulent flow. Think about the developing length in turbulent flow. You go back and look in your notes and see if you can find where I wrote down how long does it take for a turbulent flow to become thermally fully developed. It's 10 times the diameter. Okay, so that's what this basically says. They're saying this correlation applies when the flow is mostly fully developed, right? So you've basically got, like, of course there's an entry region, but the tube is long enough that it's been fully developed over most of its length. So that applies to us as well. The only other thing we have to check is the Prandtl number. And we weren't given the Prandtl number directly in our information. So we have to go check that, but I can tell you for oils, the Prandtl number is, we're gonna be okay, I think, here, right? For the oil that we have. So I just go grab this correlation, yeah, and I apply it. So if I grab it, we're saying the Nusselt number is 0.023 times the Reynolds number to the 4/5 times Prandtl to the 0.4, and that's equal to H times D over the fluid thermal conductivity. So I can calculate H from this. Okay. I've already calculated the Reynolds number. What we don't have yet is the Prandtl number, and I wasn't given it directly. So in this case, we'd have to do some work. And remember that this is defined as the ratio of the kinematic viscosity to the thermal diffusivity. And if you plug in how these are related to other things, you can show that the Prandtl number is also the heat capacity of the fluid times the dynamic viscosity over the fluid thermal conductivity. And you can get that if you remember that this is the kinematic viscosity over the density, and this thermal diffusivity is A over rho C, hopefully. Okay, I'm sure this is right. I'm not sure this is right. I might have that inverted. Okay, anyway, you plug all that in, and you calculate for your Nusselt number that you have 1,062 for the Nusselt number. And you take that Nusselt number, right, and you use it to calculate the convection heat transfer coefficient. You take the 1,062, you multiply by the fluid thermal conductivity, which we were given for this fluid. You have to go look it up if you weren't given it, over the 0.07 meter, and you get H is 1,183 watt per square meter Kelvin. So now we have H, and we can go back to our Newton's law of cooling, and we ask the question, what's the surface temperature at the exit, right? So you just solve this thing for surface temperature. It's the flux over the convection heat transfer coefficient plus whatever your mean temperature is at the location that you want to know the surface temperature, right? Because they go together. So this is the mean temperature at the location where I want to know what the surface temperature is. So we calculated that. So I take my 20,000 watt per square meter, divide by this 1,183 watt per square meter Kelvin, and I add the mean temperature that we calculated for the exit, 412 C. Watt cancels, meter squared cancels. This Kelvin is a difference in temperature, and so it's actually also you can think of it as a degree C. So I'm going to take degree C and add the degree C. We have 428 degrees C here. That's it. So it's not that different, right, than the average temperature of the fluid. It's only, what, 10, 14 degrees higher. The surface temperature is 14 degrees higher than the average, the mass average temperature of the fluid. But this also represents the max temperature of the fluid. Right? So that seems, I don't know, reasonable. All of this, right, all of this only applies, right, to conditions in which we know the flux and it's given.